Carbonyl compounds are polarized because the oxygen is more electronegative than the carbon and it draws electron density to it. So in organic chemistry we express that as resonance structures involving one form with an anion on the oxygen and a cation on the carbon. In the presence of nucleophiles, carbonyl compounds react in such a way that the electron density can be transferred from the nucleophile on to the carbonyl oxygen via breaking a double bond of the C to O. But the reaction is potentially reversible. How do we tell which reactions are reversible and which ones go irreversibly to product? Well, if the nucleophile is extremely stable, it will not be inclined to react in this way, and the aldehyde will be unreactive with that particular reagent. However, if the nucleophile is unstable, then it will tend to be more reactive and we will get the alkoxide product. How can we predict whether a nucleophile is going to be stable or not? Well, one way to do this is to look at the acidity of the conjugate acid. If the protonated form of the nucleophile readily dissociates into a proton and the nucleophile, then that's a strong acid. The K value for a strong acid will be big and the pKa value will be small. On the other hand, if the conjugate acid of the nucleophile does not dissociate readily, then the nucleophile will be unstable, the K value will be small, and the pKa will be large. Let's consider what happens when we take hydride nucleophile and react it with an aldehyde like formaldehyde. Hydride has a conjugate acid, dihydrogen H2, pKa 35. So hydride anion is unstable. If we can find a reagent that delivers hydride, it will deliver it to the carbonyl irreversibly and we will get the alkoxide of methanol. Similarly, if we take a methyl anion, the conjugate acid is methane, the pKa of methane is 48, so a methyl anion will add readily to aldehydes and ketones, for instance to ethanal, and we will generate an alkoxide, and then on aqueous workup after the reaction is complete, addition of a source of protons will generate the alcohol. That reaction is irreversible. On the other hand, if we take chloride, chloride has an acid with a pKa of -7, that's hydrochloric acid. So chloride is an extremely stable nucleophile. It doesn't tend to add to an aldehyde like benzaldehyde or any other. If an adduct does form, it reverses straight away. There are other acids with intermediate pKa values. Hydrozoic acid is not that strong and not that weak. Azide is quite a stable anion. It might add to a carbonyl like propanal, but then the adduct is unstable, decomposes. Quite similar though is hydrogen cyanide, pKa 9.2. Cyanide will add to an aldehyde or a ketone like acetone and it will form an alkoxide. If we protonate that, we will get a cyanohydrin, and that is moderately stable. In other words, there will be some reversibility in that reaction. Okay, let's consider one or two examples. If we take hydride and add it to cyclohexanone, we will generate an alkoxide irreversibly, and on protonation we will get cyclohexanol. Similarly, if we take cyclopentanone and add a source of methyl minus, then we will get a tertiary alkoxide. On protonation we will get the tertiary alcohol. Overall, this mechanism is quite general. Stable nucleophiles may add, but the reaction is reversible. Unstable nucleophiles, as evidenced by the pKa, can add in an irreversible sense. The mechanism is straightforward, just two curly arrows, and it's different to reactions of aldehydes and ketones with neutral reagents under acidic conditions. And we'll consider that in some other video. Thank you for watching. This is Kevin Burgess. If you want to see more videos in this series or purchase a book on organic reactions, please visit the website www.byinquisition.org.